Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. So this video is for visually impaired students and the chapter name is Electromagnetic Spectrum Absorption Spectra from Organic Chemistry. Let's start. First we will talk about the introduction of the chapter. One of the most important areas of interest of an organic chemist is to determine the structure of organic compounds, whether isolated from natural sources or prepared in the laboratory. The procedure generally employed consists of the following steps: A. Purification. B. Detection and estimation of elements. C. Determination of molecular mass. D. Calculation of the molecular formula. And E. Determination of the structure. Till recently, the structures of organic compounds were mainly determined through their chemical reactions, degradations, and chemical synthesis. This process is quite tedious and time consuming. However, during the last 3 decades, a large number of physical methods have been developed which serves as powerful tools for the determination of structures of organic compounds. Of these, the most commonly used powerful tool method are the spectroscopic methods such as ultraviolet, infrared, nuclear magnetic resonance spectroscopy, and mass spectroscopy. The molecular mass and molecular formula can be determined by the use of mass spectroscopy. The nature of the functional groups present in an organic compound can be determined by combination of UV and IR spectroscopies. The complete structure, including the stereochemistry of the organic compound, is then determined by the use of NMR spectroscopy. These spectroscopy methods of structure elucidation are preferred over the classical methods because of the following advantages. These require only a small amount of 2 to 5 mg of the organic compound. These methods require a much smaller time and the information is obtained on the chart which serves as the permanent record. During most of the spectroscopic studies except mass spectrometry, the compound remains unaffected chemically and hence can be recovered. Most of these methods are extremely sensitive to small changes in a spatial orientation of the various atoms present in a molecule and hence are generally used to determine the stereochemistry of organic compounds. These methods are also useful for determining the mechanism and rates of chemical reaction. In this chapter, we shall discuss the basic principle and applications of some of the most commonly used spectroscopic methods in organic chemistry. So, the topic is electromagnetic radiations. Visible light is a form of energy which can be described by two complementary theories, that is, particle theory and wave theory. Neither of these two theories can be explain all the properties of light. Some properties of light, such as photochemical effect, black body radiations, can be explained only by the particle nature, whereas other properties of light, such as diffraction, interference, etc., can be explained only on the wave theory. In this chapter, we are only concerned with the wave nature of the light, which is briefly discussed below. Electromagnetic wave theory. Wave theory of light was put forwarded by James Clerk Maxwell in 1864. According to this theory, energy is emitted from any source such as heated rod or tungsten filament or an electric bulb continuously in form of waves or radiations, and the energy thus emitted is called radiant energy. The most commonly example of radiant energy are heat, light, x-rays, gamma rays, etc. Each radiation consists of mutually perpendicular oscillating electrical and magnetic fields, both of which are perpendicular to the direction of propagation of the radiation. In other words, radiations are associated with both electric and magnetic fields and hence are called electromagnetic radiations. All radiations have wave character and travel with the velocity of light, that is 3 into 10 raised to power 10 centimeter per second or 3 into 10 raised to power 3 meter per second. Some important characteristics of electromagnetic radiations. Wavelength. It is defined as the distance between two consecutive crests or troughs. It is generally represented by the Greek letter lambda, and it is expressed in the number of units such as angstrom, micron, millicron, and nanometer. Frequency. It is defined as the number of waves which pass through a given point in 1 second. It is represented by the Greek letter mu and is expressed in the terms of cycles per second or hertz or simply as uh, second inverse. Velocity. The linear distance which a wave travels in 1 second is called velocity. It is represented by the letter c and is expressed in the terms of centimeter per second or meter per second. Wave number. It is defined as the number of waves present in 1 centimeter length, or simply as the reciprocal of the wavelength, and represented by the symbol mu bar. Electromagnetic spectrum. The field of spectroscopy deals with the study of absorption or emission of electromagnetic radiations. We are familiar with a number of different types of electromagnetic radiations, such as um, we are familiar with a number of different types of electromagnetic radiation, such as cosmic rays, gamma rays, X-rays, ultraviolet light, visible light, infrared rays, microwaves, radio waves, radar waves, etc. All these um, all these radiations travel with the same velocity, that is 10 to 10 raised to power 10 centimeter per second, but differ from one another in the wavelength or frequency of their waves. The arrangement of all types of electromagnetic radiations in the order of increasing wavelength or decreasing frequency is called the electromagnetic spectrum. What is spectroscopy? Spectroscopy may be defined as the interaction of matter with electromagnetic waves radiations so that energy is absorbed or emitted in accordance with the relation, that is del E equals to h mu, where h is the Planck's constant, mu is the frequency of the radiation, and del E is the energy difference between the initial and the final state of the matter. Types of spectroscopies. The field spectroscopy can be broadly divided into two categories. First one is emission spectroscopy and the second one is absorption spectroscopy. So first we will discuss about the emission spectroscopy. When atoms or molecules are subjected to intense heat or an electric discharge, they absorb energy and get excited. During this excitation, the electrons in the ground state of the atom or molecule are excited to some higher energy state. Since the lifetimes of these excited states is short, so they return to some lower excited state or ground state, and the absorbed energy is released as light. When this emitted radiation is passed through a prism, it gives rise to an emission spectrum. In case of atoms, such a spectrum recorded on photographic plate commonly appears as bright lines upon a dark background, whereas molecules give to rise to bands. Absorption spectroscopy. If electromagnetic radiation is allowed to pass through the transparent medium, some is reflected, some is absorbed, and the remainder transmitted. When transmitted light is passed through a prism or grating, an absorption spectrum is obtained. The spectrum indicates those portions of the incident light that have been absorbed by the medium. Um, for example, when sodium flame is examined by the spectroscope, it reveals the presence of two yellow lines called D1 and D2, corresponding to wavelengths which is 5890 angstrom and 5896 angstrom, respectively. These two yellow lines constitute the emission spectrum of sodium. However, when the same sodium flame is placed in the path of an arc light, the spectroscope reveals the presence of all the spectral lines of the white light except for the two lines corresponding to the wavelengths D1 and D2, which are now found missing, and two dark lines appear in their place. These two dark lines constitute the absorption spectrum of sodium, whereas emission spectroscopy is useful for the study of atoms. Absorption spectroscopy is generally used for the determination of structure of organic compounds. This is due to the reason that the most of the organic compounds are not stable under the drastic conditions necessary to record an emission spectrum. Therefore, it is in this unit we shall discuss only the absorption spectroscopy. So the main topic is absorption spectroscopy. Depending upon the type of the electromagnetic radiation absorbed, the field of absorption spectroscopy can be divided into following types: UV visible, infrared, microwave, nuclear magnetic resonance, electron spin resonance. However, in this unit we shall study only UV and IR spectroscopies. Units used in various absorption spectroscopies. These uses of different spectroscopic techniques use different units of measurement of wavelength. In the ultraviolet and visible spectroscopy, the unit of measurement of wavelength is millimicrons or nanometers. In the infrared spectroscopy, the units of measurements are microns or micrometers. Um, Ultraviolet and visible spectroscopy. The UV region of the electromagnetic spectrum extends from 100 to 400 nanometer, while the visible region extends from 400 to 800 nanometer. The UV region is further divided into two separate regions. The extending from 100 to 200 nanometer is called the UV region, while the extending from 200 to 400 nanometer is called near UV region. The subdivision is necessary for practical reasons. Um, at or below 200 nanometer, uh, or to absorb strongly therefore measurements in the region are done by flushing the instrument with nitrogen. However, at 150 nanometer or below and to starts absorbing, therefore the region below 150 nanometer can be studied only by using affected instruments. That is why the region below 150 nanometer is called the vacuum region. Principle: where UV or visible radiation is passed through the solution of an organic compound, it is either absorbed or transmitted depending upon its wavelength and the molecular structure of the organic compound. As a result of absorption of energy, an electron gets excited from the ground electronic state to some higher electronic state. During this absorption process, some of the molecules of the organic compound will collide with the photons of the radiant energy. Although a large number of such photon molecule collisions are possible, but only those will result in absorption of energy in which the energy of the photon exactly matches the difference in energies of the electron in the ground state and the excited state also of the molecule. Um, Thus, if the UV radiation used has a wavelength of 286 nanometer, it corresponding to an energy of 4.18 raised to into 10 raised to power 5 joule mole inverse, as given above. Laws of absorption: the absorption of radiant energy by molecules is governed by the following two laws: Bohr's law, Lambert's law. The first one is Bohr's law. It states that the amount of light absorbed is proportional to the concentration of the absorbing solute or the number of absorbing molecules present in the medium, and that each molecule absorbs the same fraction of incident light regardless of the concentration. And the second law is Lambert's law. It states that the fraction of light absorbed by a homogeneous medium is independent of the intensity of the incident light, and that each successive unit layer of the medium absorbs an equal fraction of the incident upon it. Combining both of the laws, the following chemical empirical expression called Bird-Lambert's law may be formulated as log I naught upon I equals to molar absorptive extension coefficient into concentration into length, which would be equal to absorption. Limitations: the Bohr-Lambert's law is rigorously obeyed when a single species gives the observed absorption. However, the law is not obeyed when different forms of the absorbing molecule are in equilibrium. For example, keto-enol tautomers, solute and solvent form complexes through some sort of association. There is a thermal equilibrium between ground electronic state and a low-lying excited state. Fluorescent compounds or compounds changed by irradiation are present. Molar absorptivity. Molar absorptivity, formerly known as molar extension coefficient, is a property of a molecule undergoing an electronic transition. Its magnitude depends upon probability of the transition and the size of the absorbing system. The typical values of molar absorptivity vary from 0 to 10 raised to power 6. Value above um, are 10 raised to power 4 are termed high intensity absorption, while value below 10 raised to power 3 are called low intensity absorptions. Instrument instrument UV visible spectrometer, an instrument used to measure the percentage of radiation absorbed or emitted when a radiation of certain intensity and wavelength range is passed through the sample of an organic compound is called a spectrometer or a spectrophotometer or a spectrometer. The modern ultraviolet visible spectrometer consists of a radiation source, a monochromatometer, a detector and amplifier, and some recording devices. The most suitable source of light in the UV region is the hydrogen or deuterium discharge lamp, while a tungsten filament lamp is used for the visible region. Most of the spectrometers are double beam instruments. The electromagnetic radiations from the light source are made to fall on a rotating quartz prism to get a continuum of wavelengths, which are then separated into radiations of individual wavelengths with the help of a number of quartz slits. The monochromatic light thus obtained is split into two beams, one of which passes through the sample dissolved in a transparent solvent and other through the solvent. The intensity of the each emergent beam is measured with photocells, and the instrument electronically subtracts the absorption due to the solvent from the absorption due to the sample. The resultant intensity signal is automatically recorded on the graph as a function of wavelength. This record of the percentage of radiation absorbed or transmitted is called the absorption spectrum. Band nature of UV spectrum. A UV visible absorption spectrum consists of a few absorption bands rather than sharp peaks as I explained below. Absorption in the UV and visible region occurs due to the electronic transitions which require a large amount of energy, while lesser amount of energy is needed for the vibrational transition and still lesser for the rotational transitions. In molecules, there are only a few electronic states. Each electronic state is associated with a number of closely spaced vibrational substates, and each vibrational state in turn has a series of closely spaced rotational levels. In principle, electronic excitation can be occur from any vibration sublevel of the ground. Electronic state, but these generally occur from V0 level of the ground electronic state because this is the most highly populated state of the molecules at room temperature. As a result of these transitions, the absorption spectrum of the molecule in the vapor phase would contain a large number of closely a speed line which can be only be separated with instruments of the high resolution. However, if the UV spectra are scanned in solutions, the fine structure is generally not observed because of solvent solute interactions with which tend to smooth out the spectrum into bands. Further, even in the vapor phase, the ordinary laboratory instruments cannot make distinction between these discrete lines and hence record broad absorption bands. As a result of coalescing merging together of these absorption lines, the UV and the visible spectra of organic molecules uh, consists of bands rather than peaks. And here is the presentation of spectral data. So now we will talk about sample handling. The UV visible spectra are usually recorded in vapor phase or in a solution. For this purpose, a variety of quartz and silica cells of the path lengths between 1 to 10 cm are available. Although cells with 1 cm square area are commonly used, and these require approx 3 ml of the solution. Glass cells cannot be used since glass absorbs strongly below 300 nanometers. The cell must be thoroughly cleaned either with a detergent or a hot nitric acid before use. Um, these must be properly stored and their optical surfaces should never be touched. Solvent and solutions. The UV or visible spectra are usually measured in dilute solutions. For this purpose, a few mg of the organic compound are dissolved in a suitable solvent. A good solvent for recording the UV spectrum of any organic compound must fulfill the following criteria, which is it should be transparent in the wavelength range being examined, that is, should not absorb UV radiations in the same region as the substance whose spectrum is being determined. A large number of solvents are available for the recording UV spectra. Some of these, along with their lowest cutoff points or the lowest transparency limits, are given in table. Of the solvents listed in table, ethanol and hexane are the most commonly used since each one of them is transparent in the region of UV where interesting absorption bands from organic compounds are likely to occur. In, so the here the types of transitions are also described. It should have no effect on the fine structure of an absorption band. So now we will talk about the and it should not change the wavelength of absorption of any absorption band. Now we will talk about the types of electronic transition. The absorption of radiant energy by organic compounds in the UV and visible regions occur due to the excitation of electrons from bonding or non-bonding molecular orbitals to the anti-bonding molecular orbitals, which are usually vacant in the ground state in the molecule. The various types of electrons which are present in molecule are uh, si- uh, sigma to pi and n bond sigma pi and n bonding anti-bonding molecular orbital associated with sigma electrons is sigma star with pi is pi star, while the n electrons are not associated with antibonding molecular orbitals since they are not involved in the bond formation. So pi to pi star transition in which the electron is excited from pi bonding molecular orbital to pi star antibonding molecular uh, orbital are called pi to pi star, sigma to sigma star transition. These transitions are shown by only those compounds in which all the electrons are involved in sigma bond formation, that is saturated hydrocarbons. These require very high energy, therefore these transitions occur all short wavelengths or high frequency and are usually found in the vacuum or for ultraviolet region. For example, methane absorbs at 125 nanometer and propane at 135 nanometer. Cycloalkanes generally absorb at a higher wavelength than their corresponding open chain isomers. For example, cyclopropane absorbs at 195 nanometer relative to propane, which absorbs at 135 nanometer. This is due to the reason that because of the angle strain, the ground state energy level of cyclic hydrocarbons is higher than the corresponding saturated analogs. Analogs and 2 pi star transitions in which a non-bonding electron is excited to pi sigma star antibonding molecular orbital are called into sigma star transitions. These transitions occurs in those compounds which contain heteroatoms such as oxygen, nitrogen, sulfur, halogens, etc. For example, alcohol, ethers, alkyl halides, amines, aldehydes, and ketones. This type of transition, these transitions require lower energy than sigma to sigma star transitions and hence occur at longer wavelengths than sigma to sigma star transitions. In fact, the energy required for these transitions depend upon the electronegativity of the heteroatom. Lower the electronegativity, higher the wavelength of absorption. For example, methyl chloride absorbs at uh, 173 lambda max, while methyl iodide at 258 lambda max. This is due to the reason that the chlorine has higher electronegativity than iodine, and hence an electrons on chlorine atom are comparatively difficult to excite than on iodine atom. Similarly, amines absorb at longer wavelengths than alcohols because of lower electronegativity of nitrogen as compared to oxygen. For example, methyl alcohol absorbs at 195 nanometer and methyl amine absorbs at 227 nanometer. The fact that the absorption at 227 nanometer in trimethylamine is actually due to the N to pi star transition is proved by the observation that when its spectrum is scanned in aqueous acid solution, it doesn't show any absorption. This is due to the reason that in acid solution the amine gets protonated. As the result, the N electrons are not available since they are now involved in bond formation. Pi to pi star transitions in which a pi electron is excited to an antibonding pi star molecular orbital are called pi to pi star transitions. The type of transition occur in unsaturated compound containing double and triple bonds and also aromatic compound. These transitions generally require a large amount of energy and hence occur at the uh, short wavelengths. For simple organic compounds containing isolated unsaturated centers, the absorptions uh, of these transitions is usual. The absorption to of pi to pi star transition occur well outside the range of ordinary spectrometers, but the intensity of these transitions is usually very high. For example, in saturated aldehydes and ketones, the pi to pi star transition produce an absorption band of high intensity at about 185 nanometer. Similarly, unconjugated alkenes such as ethylene absorbs at 175 nanometer, and simple alkynes such as acetylene absorbed around 170 nanometer. So it may be mentioned here that the position of pi to pi star transition is sensitive to substitution on doubly bonded carbon atoms. In general, the presence of one Ni group on the double bond produces a bathochromic shift of 5 nanometer. A bathochromic or red shift, as it is also means a shift to lower frequency and longer wavelength. And to pi star pi star transition in which an electron is excited from non-bonding atomic orbital to the pi star molecular orbital called n 2 pi star transitions. All organic compounds containing a double bond between carbon and some heteroatoms such as C double bond O, C double bond S, N double bond etc. show this type of transition. Out of all the transitions discussed above, N to pi start requires the minimum amount of energy and hence occurs at longest wavelength well within the range of ordinary spectrometers. However, the intensity of absorption of N to pi star transitions is very low. For example, the carbonyl group of a saturated aldehydes and ketones shows a weak absorption due to N to pi star transition around 280 to 290 nanometer. The low intensity of this band will be explained in the next section. Selection rules. Certain electronic transitions which at first sight appear to be possible are generally do not observe. This is because certain restriction called selection rules given these electronic transitions. These are listed below. Transitions which involve a change in the spin quantum number of an electron during the transition state do not occur. In other words, direct singlet triplet transitions are forbidden. Transitions between orbital of different symmetry usually do not occur. For example, N to pi star transition is symmetry forbidden. Transition probability. The magnitude of the molar extinction coefficient is the measure of the probability of a particular electronic transition. Depending upon the values of extinction coefficient makes transitions are of two types: allowed transitions, forbidden transitions. Transition having a mix between 10 raised to power 4 to 10 raised to power 5 are called allowed transitions. These are generally due to pi star transitions, and transitions having a mix between 10 to 1000 are called forbidden transitions. For examples, the N to pi star transition of saturated aldehydes and ketones show a weak absorption between 280 to 290 nanometer, Emax less than 100. One on the other hand, N to pi star transitions are symmetry forbidden. Symmetry forbidden does not mean that it never occurs, but implies only that its probability is very low. The low probability of N to pi star transition is due to the fact that N electrons on the heteroatom are in plane perpendicular to the pi star molecular orbital. Since the regions in space of these two orbitals overlap only poorly, the probability of excitation of the n electron to the pi star orbital is quite low. Nevertheless, N to pi star transition does occur. This is due to the twisting of the molecule in the excited state, which increases the overlap. This, although the N to pi star transition is symmetry forbidden, but the vibrational interaction makes the transition partially allowed. Solvent effects. The polarity of the solvent usually shifts the position of an absorption band either towards longer wavelength towards shorter wavelength depending upon the type of electronic transition involved as below. Uh, N to pi star and to N to sigma star transitions. If a group is more polar in the ground state than in the excited state, the N electrons in the ground state are stabilized relative to the excited state due to the hydrogen bonding or dipole-dipole interactions with the polar solvents. Um, if a group is more polar in ground state than in the excited state, the n electrons in the ground state are stabilized relative to the excited state due to their hydrogen bonding or dipole-dipole interactions with the polar solvent. As a result, the energy difference between the excited state and the ground state increases, and hence the absorption shifts towards the shorter wavelength as shown in figure. This shift is the absorption. H bonding or dipole-dipole interactions will be lower the energy of the ground state more than that of the excited state, and hence the absorption shifts to the shorter wavelength. Pi to pi star transitions. If a group is more polar in the excited state than in the ground state, the H bonding and dipole-dipole interactions with the solvent will stabilize the excited state more than the ground state. As a result, the energy gap between the ground and the excited state decreases and the absorption shifts towards longer wavelength. Consider, for example, ethylene molecule in the ground state. The pi electrons are almost equally distributed between the two carbon atoms, and hence the molecule is non-polar. But in the excited state, one of these carbon atoms becomes electron deficient and the other electron rich. As a result, the molecule is more polar in the excited state. Simple chromophoric groups. The term chromophore was originally applied to a system which imparts color to a compound. For example, nitro group is a chromophore since it imparts yellow color to the compound. So, the term chromophore is used in a much broader sense. Thus, a chromophore is now defined as any functional group that absorbs electromagnetic radiations irrespective of the fact whether it imparts color or the to the compound or not. For example, a carbonyl group is a chromophore since it absorbs the UV region at around 279 nanometer with a molar extension coefficient about 15. Some of the important simple organic chromophoric groups along with their approximate lambda max and max are given in the table. Uh, Chromophores such as C double bond C and C triple bond C, which contains pi electrons and hence undergoes pi to pi star transitions. Chromophores such as C double bond O and double bond N, not O, etc., which contain both pi and n electrons, undergoes pi to pi star and n to pi star transitions. Further, if a number of organic compounds have the same functional group or chromophoric group, all these compounds will generally absorb at very nearly the same wavelength lambda max and will have very nearly the same molar extension coefficient. Therefore, it is possible to determine the functional groups present in a molecule by comparing its UV spectrum with the data given in the literature for known compounds. uh, Auxochromes, groups which themselves do not show any characteristic absorption above 200 nanometer but which when attached to a given chromophoric usually cause a shift of absorption bond to longer wavelength uh, with a simultaneous increase in the intensity of the absorption band are called auxochromes. Some common examples of exochromic groups are OH, NH2, SH, etc. In other words, the shift towards longer wavelength. So, the mechanism of the action. One of the characteristic features of all auxochromes is that they contain non-bonding electrons. The non-bonding electrons extend the conjugation of the chromophore by sharing of the non-bonding electrons as shown below. In other words, the shift towards longer wavelength, that is bathychromic effect produced by auxochromes, is due to the extended conjugation. It will be discussed in the next section that the effect of extended conjugation is to reduce the energy difference between the ground and the excited state. As a result, the absorption shifts to the longer wavelength with simultaneous increase in the intensity of the absorption band. Change in position and intensity of absorption band. Um, Bathychromic shift or red shift. The shift of absorption maxima to longer wavelength is called bathychromic shift or the red shift. This can be achieved by the following three ways: by attaching an auxochrome to the carbon-carbon double bond or the benzene ring, as discussed above. Placement of an auxochrome such as ethoxy group at para position of trans azobenzene shifts its longest wavelength absorption band by 65 nanometer to longer wavelength and also increases its intensity to fall, that is auxochrome such as NH2 group shifts its primary absorption band from 203.5 nanometer to 234. This bathychromic shift due to the interaction of the pi electrons of the auxochrome with the pi electrons of the benzene ring, thereby substituting the excited state. As a result, the energy gap between the excited state and the ground state decreases and the absorption shifts no longer wavelength to longer wavelength. Furthermore, the availability of n electrons greater is the bathychromic shift since O is more electronegative than N. Therefore, the lone pair of electrons on N are more easily available for the interaction with pi electrons of the benzene ring than those on the O atom. As a result, bathychromic shift is expected to be longer in aniline than phenol. For example, in going from benzene to phenol, the primary bond shifts from 203.5 nanometer to 210.5 nanometer, while the secondary bond shifts from 254 to 270 nanometer. In contrast, in going from benzene to aniline, the primary bond shifts from 203 to 230 nanometer, and the secondary bond shifts from 254 to 280 nanometer. Further, since the n electrons of phenoxide ion as compared to phenol are expected to be more easily available for interaction with the aromatic pi system, therefore the bathychromic shifts in the both primary and secondary bonds of phenoxide ion are expected to be larger than those in phenol. For example, in going from benzene to phenoxide ion, the primary bond shifts from 203.5 nanometer to 235 nanometer. Unlike ethoxy and amino groups, which exert their bathychromic effect through interaction of their n electrons with the electrons of the pi system, alkyl groups exert their bathychromic effect through hyperconjugation effect. Since hyperconjugation is a more weaker effect than n-pi conjugation, therefore bathochromic shift produced by alkyl groups are often small. For example, ethylene absorbs at 175 nanometer as compared to 1-butene, which absorbs at 185 nanometer. By conjugation of two chromophores, for example, ethylene absorbs strongly at 175 nanometer in the for UV region, but when two double bonds are brought in conjugation just in butadiene, the pi to pi star transition undergoes a bathochromic shift with hyperchromic effect and butadiene absorbs at 217 nanometer. By decreasing the polarity of the solvent, for example, acetone shows a lambda max at 264.5 nanometer in the H2O due to N2 pi star excitation. If hexene is used as a solvent, the absorption maximum shifts to 279 nanometer. Hypsochromic shift. This may a shift of absorption maxima to shorter wavelength is called hypsochromic shift or the blue shift. This may be caused by the following two factors: by attaching an oxychrome to the C double bond O group. For example, N2 pi star transition of the acetaldehyde appears at 293 nanometer, but it undergoes a hypsochromic shift when its H atom is substituted by an exochrome as shown below. The hypsochromic shifts of the N2 pi star transition is primarily due to uh, negative effect of the heteroatom, that is ON or Cl. These heteroatoms withdraw electrons from the carbonyl group, causing the lone pair of electrons on the carbonyl oxygen atom to be held more firmly than they would be in the absence of the inductive effect. As a result, the energy of n orbital decreases more than that of the pi star orbital. In other words, energy gap between n to pi star orbitals increases, and hence the absorption shift towards shorter wavelength. By increasing the polarity of the solvent, for example, n to pi star's transition of acetone in hexane appears at 279 nanometer, but this absorption shifts to lower wavelength and appears at 264.5 nanometer in water. Uh, hypochromic effect. The effect leads to the decrease in the molar absorptivity. For the hypochromic effect, shifts are often accompanied by hyperchromic effect. For example, when benzoic acid is converted into benzoate or aniline is converted into aniline ion, both the primary and secondary bands exhibit hypsochromic shifts with hypochromic effect as shown in table. Effect of conjugation. If an organic molecule contains two or more chromophores which are separated by two or more single bonds, their effect on the spectrum is usually additive. This is due to the reason that there is little electronic interaction between these isolated chromophoric groups. However, when the two chromophoric groups are conjugated, that is, are separated by one single bond, a large effect on the spectrum is produced. Since the pi electron system is now spread over at least 4 atomic centers. As a result, the high intensity absorption band is generally shifted 15 to 45 nanometer to the long wavelength, with simultaneous increase in the intensity of the absorption band as compared to the unconjugated chromophores. Similarly, when a carbonyl group is brought in conjugation with a double bond with the pi to pi star and n to pi star, absorption bonds are shifted to longer wavelengths. Some conjugated chromophoric groups are in given below the table. Let us discuss the effect of conjugation on the absorption spectra of dienes and palenes and alpha beta unsaturated carbonyl compounds. Conjugated dienes, cyclic dienes, simple alkenes such as ethylene absorbs at 175 nanometer, but when two double bonds are brought in conjugation, as in 1,3-butadiene, the pi to pi star absorption band shifts to 217 nanometer with a simultaneous increase in extinction coefficient mix. This may be explained as follows. A double bond consists of two pi molecular orbitals, one bonding and the other anti-bonding. But when two double bonds are brought in conjugation, four molecular orbitals are formed. Two of these, that is pi 1 and pi 2, are bonding and are occupied by pair of electrons each, while the other two anti-bonding, that is pi 3 and pi star 4, as shown in figure. Thus, it is clear that the energy of the highest occupied molecular orbital, that is pi 2, increases while that of the lowest unoccupied molecular orbital decreases. As a result, the energy levels involved pi to pi star transition now come closer to, hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 orbitals in 1,3-butadiene is more lower than the corresponding gap between pi and pi star orbitals in ethylene, and hence 1,3-butadiene absorbs at a longer wavelength than ethylene. Further, since the energy levels come closer, their interaction in the excited state increases, and hence extension maximum also gets up. Um, In a similar way, we can show that when three bonds are brought into the conjugation, energy between the HOMO and LUMO becomes still smaller, and the pi to pi star absorptions ensure a further pathogrammic shift with a further increase in the emics of the absorption band. Cyclic dienes. Cyclic dienes are of two types: homoannular dienes and heteroannular dienes. Homoannular dienes, conjugated dienes in which the two double bonds are present in the same ring, are called homoannular dienes. Due to the rigidity of the ring system, these dienes necessarily exist in the S-cis orientation. Uh, Heteroannular dienes. Conjugated dienes in which the two double bonds are present in different rings are called heteroannular dienes. Due to the rigidity of the ring system, these dienes necessarily exist in the S-trans orientation for some reasons discussed under cyclic dienes. Homoannular dienes absorb at longer wavelength but with lesser intensity as compared to heteroannular dienes, which absorb at shorter wavelengths but with the higher intensity. Effect of endocyclic and exocyclic bonds on the absorption maxima of dienes. A double bond is said to be exocyclic if it lies within a particular ring, and exocyclic if it lies outside a particular ring. Consider, for example, the following compounds. Compound 1 contains two double bonds, both of which lie within rings and hence are called endocyclic double bonds. Compound 2 also contains two double bonds. The double bond between C1 and C2 lies within the ring and is called the endocyclic double bond, whereas the double bond between C3 and C7 lies outside the ring and is called exocyclic double bond. It is interesting to note that the same double bond can be exocyclic to one ring and endocyclic to other. For example, consider compound third. Ring A contains one double bond C3 C4 and it thus endocyclic. Ring B contains two double bonds, that is B C3 C6 and C7 C8. Both of these are endocyclic to ring at the same time. From C5 to C6 double bond is exocyclic to ring A, and C7 to C8 double bond is exocyclic to ring C. In general, each exocyclic double bond increases the wavelength of absorption of green cyclic conjugation given cyclic conjugated diene or polyene by 5 nanometer. The reason for this small pathogrammic shift is then an exocyclic double bond dissolves. The strainless suggests a staggered conformation of the chair form of cyclohexene more than does an endocyclic double bond. As a result, the energy of HOMO is raised. In other words, the energy gap between HOMO and HOMO decreases, thereby shifting the absorption towards longer wavelength. Woodward-Fisher rules for calculation of lambda max of simple conjugated dienes. Woodward formulated certain empirical rules for calculating the lambda max for the long wavelength pi to pi star transition for dienes and polyenes. These rules were later modified by Fisher in 1959. According to these rules, each diene has a certain fixed basic value, and the value of lambda max depends upon the following points. First one is the number of alkyl substituents or ring residues present on the diene system. Second one is the number of double bonds extending conjugation beyond the diene system. So the presence of polar groups or exochromes such as Cl, Br, etc. The applications of the above rules are illustrated by the following examples, as the examples are given below. Linearly conjugated and cross-conjugated polyenes. If all the double bonds of conjugated polyene lie along a single continuous path, the polyene is to be linearly conjugated, and if on the other hand all the double bonds do not lie on the single continuous path contain branch conjugated system, the polyene is said to be cross conjugated. Consider for whereas tetraene is linearly conjugated since all the four double bonds lie along a single continuous path. On the other hand, triene is a cross conjugated since all the three bonds are double bonds. Bonds do not lie along a single continuous path. Such a system can often be resolved in two or more partial linear conjugated system for the purpose of calculating lambda max. The empirical rule suggests that the calculation be made on that partial line system which absorbs at the longest wavelength. Thus, for the linearly conjugated tetraene, the rules predict lambda max that would be 353 nanometer, which is excellent agreement with the observed value 355 nanometer. In contrast, triene is cross-conjugated. It can be resolved into two linear conjugated dienes, one heteroannular diene with the one double bond in rings B and C, the other homoannular diene in which the two double bonds are present in ring C. Since homoannular diene absorbs at longer wavelength than an heteroannular diene, therefore the calculating the lambda max of triene, homoannular diene in system is considered as the parent diene and the double bond in ring B is neglected. Accordingly to the calculated value is 288 nanometer, which is an excellent agreement with the absorbed value, that is 285 nanometer. UV spectra of unsaturated ketones, anodes. The UV spectra of unsaturated carbonyl compounds in which the double bond and the carbonyl group are not conjugated are simple summations of the absorption of the ethylene and carbonyl chromophores. In ethylene, the absorption occurs in the far ultraviolet region, and due to the pi to pi star transition, which being symmetry allowed is quite intense. The simple isolated carbonyl group gives rise to two bands as shown in figure. The short wavelength pi to pi star transition band is quite intense, that is symmetry allowed, but it lies the far ultraviolet region, much below the usual cut-off limits of the solvents, and hence is generally not observed. The second law, wavelength pi to pi star transition is weak, band is weak, that is symmetry forbidden, but usually observed since it lies much above 280 nanometer, the usual cutoff limits of the solvents. However, when C double bond C and C double bond R gramophores are conjugated, both N to pi star and pi to pi star transitions are shifted towards longer wavelength. For example, methyl oxide and alpha beta unsaturated ketone shows lambda max at 230 nanometer due to the pi to pi star transition, and lambda max at 329 nanometer. The energy level diagram of an alpha beta unsaturated carbonyl group is shown in figure. The diagram is, however, more or less similar to that of butadiene as shown. It is evident from figure that the energy of homo or alpha beta unsaturated carbonyl compound, that is pi 2, that is pi 2 is higher than the pi orbital of the ethylene or the carbonyl chromophore. Similarly, the energy of the LOMO and the alpha beta unsaturated carbonyl compound is lower than the energy of the pi star orbital of the ethylene or the carbonyl chromophore. Hence, the pi to pi star transition of the alpha beta unsaturated compound is shifted towards longer wavelength. Since pi 3 is lower than pi star of the isolated carbonyl, the promotion of one of the oxygen lone pair electrons N to pi 3 bonding requires less energy than the similar promotion in the isolated carbonyl group, and hence the N to pi star transition is also shifted towards longer wavelength. Woodward-Fisher rules for calculation of lambda max for pi to pi star absorption band of alpha beta unsaturated carbonyl compounds anodes. We have discussed above that when a double bond is conjugated with a carbonyl group, it gives two absorption bands: an intense absorption band in the region 220 to 250 nanometer due to pi to pi star transition, and a weak absorption in the region 310 to 330 nanometer due to the N to pi star transition. While the pi to pi star transition is affected in the predictable manner by structural modification of the chromophore, N to pi star transition does not show this predictable behavior. Woodward and Fisher examined the UV spectra of a number of alpha beta unsaturated compounds in ethanol and formulated a set of empirical rules in which help us to predict the lambda max of pi to pi star transition in an unknown compound. These rules are summarized in table 9.6. Solvent correction. Since pi to pi star absorption band is strongly affected by polarity of the solvent, therefore to convert lambda max value obtained in another solvent to standard ethanol solvent, the following solvent corrections have been proposed. um, Base values: alpha beta unsaturated acyclic or 6-membered ring ketone, the value would be 215 nanometer. For alpha beta unsaturated 5-membered ring ketone, the value would be 202 nanometer. For alpha beta unsaturated aldehydes, for 207 nanometer. Alpha beta unsaturated acid or esters, 197 nanometer. Increments: each alkyl group or ring residue 10 nanometer on alpha, 12 nanometer on beta, and gamma and higher 18 nanometer. Each double bond extended conjugation 30 nanometer. Each exocyclic doubly bond 5 nanometer. Homoannular diene component 39 nanometer. Oxochromes at alpha position 35 nanometer, at beta 30 nanometer, gamma 30 nanometer. Oxochromes like hydroxy and at delta it would be 50 nanometer. These rules are illustrated by the following examples as which are given below. Linearly and cross-conjugated anones. If the two or more double bonded bonds lie only on the side of the keto group, it is said to be a linearly conjugated anion, and if on the other hand one or more double bonds lie on either side of the keto group, it is said to be a cross conjugated anion. For example, structure 1 represents a linearly conjugated dianion, while structure 2 represents a cross conjugated dianion. Thus, a cross conjugated dianion contains a branch chromophore. Such systems contain two overlapping alpha beta unsaturated cationic chromophores, each one of which will give its O1 pi to pi star absorption band with a high extension coefficient, but due to the bad nature of the spectra, only that alpha beta unsaturated cationic chromophore which absorbs at longer wavelength with higher intensity is usually observed. In other words, across conjugated systems, the longest wavelength absorption band is due to the most highly substituted simple conjugated system present. For example, consider the steroidal anions. Dianion may be regarded to consist of two alpha beta unsaturated chromophores A and B as shown by dotted lines, whereas dianion A has only a beta substituent. Dianion B has two beta substituents in addition to an hexacyclic double bond. Therefore, chromophore B is expected to absorb at longer wavelength, and hence, for the purpose of calculating the lambda max, we consider the most highly conjugated system B. Similarly, trianon can be considered to be made up of alpha beta unsaturated ketonic chromophores A and B, since chromophore B has two conjugated double bonds on homoannular diene component 1 alpha 1 beta and gamma ring residue. It is expected to absorb at longer wavelength than chromophore A as calculated below. The second example is also given. Applications of UV spectroscopy. Some important applications of UV spectroscopy are discussed below. Detection of functional groups. UV spectroscopy has been used to detect the presence or the absence of the certain functional groups in the organic molecules. For example, if an organic compound does not show lambda max above 200 nanometer, it cannot contain a conjugated chromophore, an aldehyde or a keto group, a benzene ring or bromine or I atom. However, it may possess F or Cl, an isolated double or a triple bond, an amino hydroxyl carboxyl ester amido cyano or a mercapto group. Distinction between conjugated and non-conjugated compounds. UV spectroscopy can be used to distinguish between the conjugated and non-conjugated compounds. For example, due to conjugation, both pi to pi star and n to pi star absorption bands in compound 1 will absorb at longer wavelength than those in compound second, as both the figure are given above. Similarly, completely conjugated and cross conjugated ions can be easily distinguished for the example which is given below. The cross-conjugated dianion absorbs at lambda max 246, while the completely conjugated dianion absorbs at lambda max 278. Distinguished from each other. Determination of extent of conjugation. One of the most important uses of UV spectroscopy is to detect and estimate the extent of conjugation in a conjugated polyene. Butadiene itself detect and estimate the extent of conjugation in a conjugated polyene. Butadiene itself detect and estimate the extent of conjugation in conjugated polyene. Butadiene itself absorbs at 270 nanometer, but addition of each double bond shifts the absorption maxima to the longer wavelength by about 30 nanometer. Greater the number of such conjugated double bonds, longer is the wavelength of the absorption. So for compounds containing 8 or more conjugated double bonds, the absorption in fact occurs in the visible region and the compound appears colored to the human eye. For example, trans beta carotene, uh, orange color pigment of carrots, which contains 11 conjugated double bonds, shows two absorption maxima at 452 nanometer and 478 nanometers. Similarly, lycopene, a compound partially responsible for the red color of the tomatoes, also has 11 conjugated double bonds and hence absorbs at lambda max 505 nanometer. Thus, by measuring the lambda max of an unknown polyene, we can determine the number of conjugated double bonds it actually contains. Detection of impurities. Compounds with large lambda max values can be detected when present as impurities at low concentration, provided the sample itself does not show any absorption in the region of impurities. A practical application is the detection of benzene present as an impurity even at low concentration in a sample of ethanol. As stated earlier in the unit, absolute or anhydrous ethanol can be prepared from commercial ethanol or certified separate spirit or azeotropic distillation with benzene using dense talc apparatus. Because of toxic nature of benzene, it is desirable that ethanol meant for the internal use must be free from benzene. The stresses of benzene, if present as an impurity uh, by ethanol can be detected by scanning its UV spectrum. If the UV spectrum of the sample shows an absorption at 254 nanometer, it contains benzene, otherwise not, because ethanol is transparent at this wavelength. The fifth application of UV spectroscopy is quantitative analysis. Due to this high sensitivity, UV spectroscopy is a valuable analytical tool. It is based upon Bohr-Lambert law, which relates absorbance A of the substance at a particular wavelength to its concentration C and molar absorptivity coefficient. A equals to log I naught upon I, which is equal to molar absorptivity constant into concentration into length. Uh, a simple example of quantitative analysis by UV spectroscopy is the estimation of a mixture of anthracene and naphthalene. The UV spectrum of an ethanolic solution of the anthracene absorbs at 375 nanometer, well above the principal absorption bands of naphthalene lambda max 275 nanometer and 312 nanometer. Therefore, to estimate anthracene, a standard solution of anthracene naphthalene is prepared and its absorption is measured at 375 nanometer. By the application of Bohr-Lambert law, the concentration of pure anthracene in anthracene naphthalene mixture can be calculated. The sixth application is determination of strength of hydrogen bonding. Polar protic solvents such as H2O, C2H5OS, that is ethanol, CH3OH, methanol, etc., are known to form H bonds with the N electrons of carbonyl oxygen. The lower the energy of the N electrons in the ground state by an amount equal to strength of the H bond. Depending upon the strength, the N to pi star transition of carbonyl compound is shifted towards shorter wavelength. Thus, by measuring the lambda max of carbonyl compound in a non-polar and polar protic solvent, the strength of the H bond can be determined. For example, N2 pi star transition of acetone in hexane occurs at 279 nanometer, but in H2O it occurs at 264.5 nanometer. The hypsochromic shift of 14.5 nanometer correspond to energy of 5 kcl mole inverse. Thus, the strength of the H bond between H2 and acetone is 5 kcl mole inverse, which is an excellent agreement with the known strength of H bonds. Seventh application is identification of geometrical isomers. UV spectroscopy can be used to distinguish between a pair of geometrical isomers. In general, trans compounds absorb at longer wavelength with higher extension coefficient than the corresponding cis isomers. For example, the trans stilbene and the cis stilbene. The reason being that in trans stilbene, the two phenyl groups are on the opposite sides of the double bond. As a result, there is no steric hindrance, and the ethylenic double bond are the pi bonds of the benzene rings and are coplanar. Consequently, more effective pi orbital overlap occurs. As a result, energy gap between HOMO and LUMO decreases, and hence pi to pi star transition of trans isomers occurs at longer wavelength. Hence, the trans isomer absorb at longer wavelength. On the other hand, the cis isomer, there is some steric hindrance due to the presence of two phenyl groups on the same side of the double bond. Consequently, the pi system is not coplanar and hence extent of delocalization decreases. Therefore, the cis isomer absorbs at shorter wavelength. Further, because of coplanarity of pi system, the length of the chromophore is much longer in trans stilbene than in cis-stilben. Therefore, trans-stilben has much higher intensity than cis-stilben. Similarly, cinnamic acid absorbs at a longer wavelength with the higher intensity, and then the corresponding cis-cinnamic acid or allocinamic acid. Eighth application is study of ketoenol tautomerism. Beta diketones and beta ketoesters are known to exist as tautomeric mixtures, and their UV spectra show absorption bands which are characteristic of both the keto and the enol forms. That is, they show two absorption bands, a strong pi to pi star absorption due to enol form, and a weak and to pi star absorption due to the keto group. For example, ethyl acetoacetate in ethanol shows a strong bond and to at 245 nanometer due to enol form, and a weak bond at 275 nanometer due to the keto form. Unlike ethyl acetoacetate, which predominantly exists in keto form, in ethanol, acetyl acetone exists predominantly in the enol form and shows a strong absorption at 273 nanometer. The unusually high value of lambda max is probably due to the chelation in the enol form. Determination of relative amounts of keto and enol forms and calculation of equilibrium constant. In general, in polar protic solvents such as H2, C2H54H, etc., keto form predominates due to stabilization by H bonding. On the other hand, the non-polar solvents such as hexane H bonding is not possible, and um, hence enol form predominates due to stabilization by intramolecular H bonding as shown below. Thus, the percentage of enol form decreases as the polarity of the solvent increases. Since the intensities of absorptions in UV spectra are functions of the concentrations of absorbing species, therefore UV spectroscopy can be used to calculate the relative amounts of the keto and the enol forms and the equilibrium constant. The seventh application is detection of formation of charge transfer complexes. It's eighth. Just 1 second. It is ninth application, not seven. Detection of formation of charge transfer complexes. Um, UV spectroscopy is quite useful in detecting the formation of charge transfer complexes are discussed below. Uh, Many electron-rich organic molecules such as aromatic hydrocarbons, phenols, and aromatic amines are known to form charge transfer complexes. Molecules such as picric acid, tetracyanoethylene, etc. During the formation of these complexes, electrons are transferred from the donor to the acceptor molecule. This results in production of two new molecular orbitals, and transition between these new orbitals give rise to a new absorption band. In fact, the appearance of this new additional absorption band is regarded as a criterion for the formation of charge transfer complex. Perhaps the best known charge transfer complexes are the hydrates of aromatic hydrocarbons, phenols, and amines, majority of which are stable and hence can be isolated and crystallized, thus serve as derivatives of above classes compounds. Charge transfer complexes which are not stable enough to isolate it can be characterized through their UV spectra. For example, when I2 is dissolved in benzene, it forms a brown charge transfer complex which absorbs strongly at 290 nanometer, while benzene absorbs at 254 nanometer and I2 absorbs in the visible region at 500 nanometer. Similarly, when TCN is added to a chloroformed solution of aniline, blue charge transfer complexes formed, which absorbs strongly in the visible region at 610 nanometer, while aniline and TCNE absorb at 280 nanometer and 300 nanometer respectively. The 10th application is study of hindered rotation and conformational analysis. UV spectroscopy has been used to study hindered rotation in a ortho-substituted diphenyls and stereochemically hindered dienes as discussed below. First is study of biphenyls. Biphenyl is not a planar molecule. The two rings are held at angle of 45 degree. If large groups are present at ortho positions, planarity is further reduced. As a result, extent of pi orbital overlaps decreases, and hence ortho substituted biphenyls absorbs at lower wavelength with reduced intensity. For example, biphenyl shows lambda max at 250 nanometer, while 2-methyl biphenyl shows lambda max at 237 nanometer. Second, a study of sterically hindered dynes as stated above. Deviation from coplanarity of double bonds will result in reduction of pi orbital overlap with the corresponding shift of lambda max to lower wavelength and reduce intensity. For example, 2 to 3 tertiary 1 3 butadiene, in which there is little conjugation between the two double bonds due to the bulky tertiary groups. Lambda max at much lower wavelength as compared to 2,3-dimethyl 1,3-butadiene, which absorbs at 224 nanometer. The last application is progress of a reaction. UV spectroscopy can be used to determine the progress of some reactions by measuring UV spectron and liquids withdrawn from the reaction mixture from time to time. For example, consider the reduction of ketone to secondary alcohol. As the reaction proceeds, the characteristics N to pi star absorption band of the ketone will start disappearing. Consider disappearing since the alcohols are transparent in the UV region. Therefore, the complete absence of the N to pi star absorption band due to the ketone shows its complete reduction to the corresponding alcohol. Thanks for watching.